Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we're delighted to have Dan Spielman from Yale with us, and he'll tell us about graph approximation and local clustering, with applications to the solution of diagonally dominant linear systems.
Thanks. Okay, so yeah, it used to be the other way around. A couple years ago, Shang-Hua Teng and I started looking at how to solve linear equations quickly. And we started following up on an approach introduced by Praveen Vijay that I'll explain to you in a few minutes. And our goal, as you'll see, is going to be to find actually nearly linear time algorithms for solving linear equations, at least from reasonable families, using tools from graph theory to do it. So in the end, we wound up using a heck of a lot of tools from graph theory to do it. And I think this is one of those rare instances where the parts are actually more than the sum. It turns out that I actually really got into the graph theory and the graph algorithms involved in this. And while I really like solving linear equations, I think that for most audiences, actually the graph theory is more interesting. So that's what I'm going to focus on in this talk. In particular, I'll talk about local clustering, I'll explain in a minute, and what various notions of what it would mean to approximate one graph by another graph that we wind up using here. Usually we're going to approximate one graph by a sparser graph. I should say also, stop me at any time with questions or whatever. There's a small audience, and I'm happy to go off on tangents if we need. So why don't I tell you first about the tools we're going to use. The first one is a notion of what it means to approximate one graph to another graph. It's wrong to say we invent it. It's really forced on us by numerical analysis. And I will explain exactly how and why in a few minutes. And then what we're going to look at is sparsification, which is taking an arbitrary graph and approximating it by a sparse graph. Now, there are different notions of sparse. The first one that comes up is approximating a graph, maybe by a graph with a linear number of edges in the vertices. Sort of like think of, well, as you'll see later, I'll say an expander graph is the right approximation of the complete graph. That I'll explain first. Then we're going to talk about approximating graphs by even sparser graphs, say by trees. And then the question is, what is the right notion here? It turns out the right notion is something called a low-stretch spanning tree. And I'll explain to you why and tell you a little about those. And actually, what I didn't put on this slide, what we're really going to use is a combination of these two ideas, which gets us a notion of approximating a graph by something that looks like a tree, plus a couple of extra edges added back in, or at least a sublinear number of edges. And that's really what we'll wind up using. As I said, we were interested in nearly linear time algorithms for doing these things. So after we had these notions, the first question was, how do we come up with them? And to do sparsification, it turned out we needed a lot of other tools. We needed some fast algorithms for graph partitioning. Now, I should say there's a heck of a lot of algorithms out there for graph partitioning. Some we can prove theorems about, some we use in practice, and the two occasionally meet. But we wanted to prove a theorem and have something that we could prove would run really quickly. The way we got at that was through a clustering algorithm. And we came up with a problem that we call local graph clustering. So I'll explain this problem to you this way. Let's imagine that you have a giant graph. Imagine the graph of everyone who's called everyone in the United States. Someone probably has that graph. And then you have a node of interest. And you want to say, tell me something about this node. What's a small cluster around this node or nearby this node? So what we wanted was an algorithm where you wouldn't look at the whole graph, where you would start from that node and start exploring the graph from around that node, and then try to output something useful. In our case, coming up with a cluster, and we wanted to find the cluster in time proportional to the size of the cluster, or just a little bit more. And I will actually I'll state this problem more precisely later in the talk. I won't actually tell you how we did it. I will tell you about an improvement upon how we did it of Andersen, Chung, and Lang, which some of you may have heard of because Reed Andersen was here recently, I believe until a few months ago. I'll talk about that. So those are the tools. OK, let me go back to my motivation, which is solving linear equations. Something I feel that's often underappreciated by a lot of my generation, especially in computer science, though a lot of computer science departments started out with this as their central problem. So the reason I'm very interested in solving linear equations is I find it to be the bottleneck computation in a lot of problems, in almost all of optimization, and in quite a good deal of machine learning. It is what is dominating the cost of a lot of computations. One reason is a lot of people just do it stupidly. They use backslash in MATLAB, which while it's great, you can always speed it up for any particular application. But also, there's a lot that hasn't, there's a lot of improvements in the field that haven't made their way into backslash. So my belief is that solving linear equations should be like sorting. It should take time nearly linear in the number of bits you need to specify that linear equation, or the number of non-zeros in your matrix, and you shouldn't hesitate to do it. Say you don't hesitate to sort your data. My belief is you shouldn't hesitate to solve linear equations. Now, are we ever going to reach this world? Probably not for general linear equations, but it is my belief that in any particular application domain where there's some characteristic of your equations, they have some structure, yes, I think this is achievable. What we're starting out with is the first family people almost always study when they're studying such things in numerical analysis. That's symmetric diagonally dominant systems of equations. And I'll explain what those are in a minute. The reason the folks in numerical analysis first study these, well, aside from many nice properties, they come up if you're doing things like solving elliptic partial differential equations by the finite element method. So they come up in scientific computing. Not everyone knows they come up in optimization. If you're trying to solve the maximum flow problem and you apply an interior point algorithm, basically what you're doing is an algorithm where iteratively you are solving diagonally dominant linear equations. That's what comes up. They also come up if you look at spectral graph theory. They come up as the Laplacians of graphs. And that's where I will start. So rather than telling you all about diagonally dominant linear equations, let me just tell you about Laplacians, and we'll focus on them for this talk. So how many of you have seen the Laplacian matrix of a graph before? OK. A lot, not everyone. So there's an isomorphism between Laplacian matrices and graphs. So if I have a weighted graph like this one here, the Laplacian matrix that comes up so much, the off-diagonal entries are negative, and they correspond to the negative weights of edges. So for example, I have an edge of weight 4 between nodes 2 and 3. So both my 2, 3, and 3, 2 entry in the matrix are minus 4. Diagonal entries in the matrix are the weighted degrees. That's set up so that if I take a look at the sum of the entries in any row or column, I get 0. This is diagonally dominant. That just means that the diagonal is at least the sum of the absolute values of the entries in the row. So the matrix might not be that illuminating. What's more illuminating is the quadratic form associated with the matrix. So in this case, you think of x as a vector assigning a real number to every vertex in the graph. So it lives in R to the vertices. And if you take a look at x transpose Lx, which is sort of one of the standard things to do with a matrix, what it is, it's the sum over all edges in the graph. OK, there's a term for each edge. You take the weight of the edge times the value of the vector at node I minus the value of the vector at node J. Well, you look at that discrepancy and you square it. So that's what this quadratic form is. And this quadratic form is usually what we'll deal with. It's very naturally associated with the graph. And it's what we'll use to leverage a notion of approximation. So when I want to tell you about approximating one graph by another graph, it's going to be related to this quadratic form. OK, this is maybe a good place to ask if there are any questions on this quadratic form. Just because, well, you'll see others. But it's the key concept. OK, so how did I get into this business? Well, I heard about this paper written by Praveen Vijay. And the soundbite I heard about it was that he was going to solve a system of linear equations in a Laplacian matrix by preconditioning with a maximum spanning tree. Now, when I heard about this, I had no idea what it meant. But I was completely amazed that a maximum spanning tree would come up at all in the problem of solving linear equations. Now, you'll see as I talk about as revealed by, so Vijay's paper was rejected from a conference. His grant proposal was rejected. We know about it essentially because he sent a manuscript to John Gilbert before he went off and started a company to solve linear equation solvers. And unfortunately, I think because of this, we lost really a brilliant mind from academia. He'd solved a number of other great problems beforehand. It was a visionary paper written around 90. So there are a couple of people who bit the bullet and actually wrote up papers explaining the ideas in it.
Did this company succeed?
Yeah, it's still in business anyway. He's got at least when I checked in a few years ago, there were some people paying him a couple $1 million a year to do this. So in the scientific computing business. There are a lot of people who want to solve linear equations quickly. He, however, has not, well, talked to us much about what we're doing now. Anyway, who knows? I don't know what he's doing in his company. So these papers I just listed in order of when they were written as opposed to when they were published. And I have a web page dedicated to all this stuff. You can find it. So let me go back to explaining what Vaidya was talking about. So first of all, I should ask, how many of you have seen the preconditioned conjugate gradient method for solving linear equations? OK, very few. So let me tell you about this, because it's what we're going to use. And it's really an amazing sort of algorithm. So we want to solve linear equations, ax equals b. B needs to be positive semi-definite. So the first idea is we're going to take A and approximate it by another matrix B. It's called the preconditioner. And then there's going to be an iterative algorithm. And in each iteration of this algorithm, you solve a system of linear equations in B, and you have to do one multiplication of a vector by A. Now, that's a very natural idea in a lot of computer science. That is, to solve a problem, you find a related, simpler problem and solve that one instead. What's different about preconditioned conjugate gradient is you can make your solutions to ax equals b as accurate as you want, only solving systems in B. So there's a number of iterations. The key point is log 1 over epsilon, where epsilon is the accuracy. This term here, square root condition number, I'll explain in a moment. That's a measure of how well A approximates B and vice versa. After that many iterations, you get a solution of accuracy epsilon, meaning the x we get minus the actual thing you want. You take a look at the norm of that vector. OK, it's an A norm. Let's not worry about that. But it's at most epsilon times the norm of what you're searching for, which is as good as you can hope for. So again, I find this an amazing idea, that by taking an approximate problem and solving the approximate problem, you can actually leverage as good a solution as you want to the original problem. I keep looking for that paradigm somewhere else. I haven't been able to do it anywhere else. But it's a remarkable thing you can do. I mentioned preconditioned Chebyshev, just another variant that we actually use in the paper. OK, so what this meant is that Vaidya was approximating the Laplacian of a graph by the Laplacian of a tree. And he took a maximum spanning tree of the graph. Now let me tell you how we're going to measure a notion of approximation. So the definition of this term, called the condition number of A with respect to B. Here's one definition that, if you do linear algebra a lot, will be familiar to you. It's sort of the maximum of vectors x of the quadratic form in A over the quadratic form in B times the maximum of the reverse ratio. These things are like what are called generalized Rayleigh quotients. For those who are used to it, this is also the largest eigenvalue of A times B inverse, if they're both positive semi-definite. And that would be the largest eigenvalue of B times A inverse. That's one definition. I find this definition awkward to work with. So let me give you another definition. For me, for another definition, it's going to amount to the same thing. We want a notion of an inequality on a graph. What does it mean for one graph to be greater than or equal to another graph? OK, so here's a definition that comes from the linear algebra. I'll say the graph H is less than or equal to the graph G. I'll give you two equivalent definitions. One is if the Laplacian of G minus the Laplacian of H is positive semi-definite. More concrete is if for all x, the quadratic form in H is always less than or equal to the quadratic form in G. If that's true for all x, then we will say that H is less than or equal to G. For example, to check if you're following, if you go back to the formula for the quadratic form, it should be easy to observe that if H is a subgraph of G, then H is less than or equal to G. Because these quadratic forms were just sums over the edges of some square. So if you drop some of the edges, it gets lower. OK, if you've got that notion of inequality. Yes?
Isn't it equivalent to saying it's a weighted subgraph?
Yes, it is equivalent to saying it's a weighted subgraph, right? You can just decrease weights on edges, and you get less than or equal to. OK, given a notion of what it means for one graph to be less than or equal to another, we can make a notion of approximation. So it turns out, if you can sandwich G between H and some kappa times H, put it between both of them, then you've got a kappa approximation. Your condition number is at most kappa. Or actually, constants here don't matter. So if I can sandwich G between a constant times H and a constant, the same constant times H times kappa, then H is a good approximation of G, and the value is kappa.
Is that just one way?
Sorry. Actually, it does go both ways. If both of the graphs are connected. There's a caveat or two, or if they have the same connected components. Yes, it's if and only if. I will always work with this later definition here. Well, probably I'll use this one in my proofs because it's easier for me to take subgraphs. I'll always approximate graphs by subgraphs, or almost always. Let me give you an example. Let's take the complete graph. Let's just look at vectors orthogonal to 1, because 1 is the all 1's vectors in the null space. If I take a look at the complete graph, this quadratic form is the identity. X transpose Laplacian of the complete graph X is always equal to n. Well, OK, n times the identity. So what's a good approximation of the complete graph? It's called an expander graph. Actually, how many of you are familiar with expanders? Good. Pretty much everyone. For those who aren't, they are the most useful thing abstract mathematicians have ever invented, in my personal view. People teach courses about them. I can't begin to say enough. Let me do say that one of the most famous examples are the Ramanujan expanders, which you can characterize this way. They're deregular graphs. And the property that they have is that for all vectors x, the Laplacian, the quadratic form in the Laplacian of the expander, is very tightly controlled. It always lives between d plus or minus 2 root d minus 1. So the eigenvalues of the Ramanujan expanders are very tightly concentrated, or the eigenvalues of the Laplacian. It's, I forgot to say x has norm 1. Yes, thank you. I knew there was something I forgot off these slides when I gave them last, but I forgot to put it back on. Yeah, x has norm 1. That's right. Thanks. OK, so what does this tell you? For the complete graph, the quadratic form is very, very concentrated. For Ramanujan expanders, it's pretty darn concentrated. This means if I take this Ramanujan expander, multiply it by n over d, then all the eigenvalues will be near n, and the quadratic form will always be near n. What does that mean? That just means reweight the edges. Multiply the weight of every edge by n over d. Then I get this nice approximation. Or, well, I guess you don't need to, but another way of saying it is that the actual graph is between something times the Ramanujan expander and something else just a little bit more times the Ramanujan expander. So for me, those expanders are the best approximations of the complete graph. OK, our goal with sparsification is to be able to do this for any graph. All that just maps to 0. And you really, because it's, so the all 1's vectors in the null space of the Laplacian. And if you add it in, it really doesn't affect anything. So yeah, you do get, this thing happens for all of them. Good question. OK, so here's what we want to do. I say one of our first goals was taking any graph and approximating it by a sparse graph. You can, again, I put up here in the quadratic form sense what that looks like. And we want to be able to do this for any graph, not just the complete graph. One thing that helped us is Banksar and Karger already did something very similar many years ago, 96, studying cut problems. They did this for all vectors in 0, 1. So you assign every xi is a 0 or 1. These are the characteristic vectors of cuts. So the idea when you take a look at this quadratic form and you put in a 0, 1 vector, so the characteristic vector of a set, whenever xi and xj are both in the set, we get 0. If neither is in the set, you get 0. When this is an edge going from inside the set to outside the set, you get 1. So the idea of Banksar and Karger's paper was they wanted to take any graph and get me another graph, which was sparse, so that for every single set of vertices, the weight of the edges leaving would be approximately the same. And this then enabled them to solve cut problems or max flow faster in graphs in time proportional number of vertices. And they showed how to do this in nearly linear time with essentially n log n, well, over epsilon squared edges via random sampling procedure. So what we needed to do was the same thing, but we don't have, our x's don't necessarily live in 0, 1. They are all real vectors. And it turns out to be a different problem, though we can take a lot of inspiration from what they did. So I'll tell you briefly what I know about this problem. Oh, we want the size of f. Oops. Yes, thank you. That should be the size of f. Thank you.
For any.
Yeah, for any graph. Can I even edit that? I won't worry about it. Do it later. Sorry. That's right. We want to get the number of edges small. OK, so if we want, and what Shang-Hua Teng and I first did was we got an algorithm where the number of edges is small but not real small. Looks like n over epsilon squared, but there's some power of log n. At least we can do that in time nearly linear in n. And I've had a team of grad students and undergrads implement heuristics for it. So we have a lot of heuristics that, well, none of the fast heuristics actually works for all graphs, unfortunately. But if you have a family of graphs, we can get you something that'll work. More recently, one of my graduate students, Nikhil Srivastava, and I came up with an algorithm that actually gets a number of edges that looks like Banksar and Karger's algorithm. I will tell you one sentence about the algorithm. People can ask me more about it later if you want, because I'll be here for a week. The algorithm is insanely simple. It's this. Compute the effective resistance of every edge in your graph. Now choose your edges n log n over epsilon squared edges, each of them with probability proportional to its effective resistance. For those who haven't seen effective resistance, you treat every single edge in your graph as a resistor, and you can just measure the resistance between 2 points. Just do random sampling with probability proportional to effective resistance. The only reason this doesn't give us a speed improvement is the question is, how do you go and compute the effective resistance of every single edge in your graph? Well, we can actually do that in nearly linear time, but it requires solving some diagonally dominant linear equations. So that's why I say this is time. You need to solve log n of them. So it's log n times the time to do a linear solve, but it actually doesn't help us for solving linear equations quickly. Yeah. We now know that we got a high-powered undergraduate, Joshua Batson, to join up with us, who I believe was here last summer, so some of you may have encountered him. And we got it down to actually a linear number of edges. So we now know these things exist with n over epsilon squared edges. We have a polynomial time algorithm for constructing them, and no clue yet how we could make it fast. But at least we know existence, which gives us a lot of confidence that one day someone will get this. OK, so that's a little about sparsification. What about solving linear equations? Because we need two things from an approximation. We need a good approximation of our original problem, but we also need to be able to solve linear equations in our approximate problem quickly. OK, so let me tell you quickly a little bit about what we know about solving linear equations. The first, completely forget about Gaussian elimination. That's nice if you want to solve one linear equation a zillion times. If you want to solve a linear equation once, there's this algorithm called the conjugate gradient, which can be used as a direct method, runs in time order mn. So if m is the number of non-zeros, n is your dimension, you can just solve linear equations in that much time. That, at least for sparse matrices, greatly destroys anything based on trying to compute an inverse. If your matrix has structure, you can solve linear equations really quickly. Like many people probably remember, if you have a tridiagonal matrix, Gaussian elimination, you do it right, runs in time order n for an n by n matrix. That corresponds to a path graph. The same thing is true of trees. If your graph looks like a tree, you can solve the linear equations in time order n. This basically looks like doing dynamic programming, where you propagate stuff from the leaves of the tree to the root and back down. If you look at what an LU factorization is doing. I'll tell you more about that in a moment. I can't resist mentioning that one of the classic results in the area was of Lipton, Rose, and Tarjan for solving linear equations in planar graphs. They have some pre-processing. It's time order n to the 3/2, but after that it's time n log n thereafter. This is based on finding graph separators. So if you can find small separators in graphs quickly and in the subgraphs, then you can solve linear equations quickly. And some of the fastest code for solving linear equations is based on stuff like this. Metis has ordering code that works doing that. That's very nice. What we will actually use is sort of a combination of these. We're going to look at linear equations that correspond to a tree plus a few edges. And I will just say for now we can solve these linear equations quickly. I'll be more precise in a minute. Let me tell you why and what's going on. So for this, I need to say a little about what happens to a graph when you do Gaussian elimination. Now, if I have the Laplacian matrix of a graph, it's a symmetric matrix. So you don't want to just do Gaussian elimination the plain old-fashioned way of doing elimination on rows. You want to preserve symmetry. This is what's called Cholesky factorization, where every time you do an elimination on a row, you also do an elimination on a column, the same column. And if you do this, there's a very nice property. The submatrices you keep getting are all Laplacian matrices if you started out with Laplacian matrices. So you're always within the realm of graph theory. And you can graph theoretically understand what happens when I take a node and eliminate its row and column. I eliminate that vertex from the graph, and I wind up putting a clique on its neighbors. OK, there's some weights on the clique, but it's a weighted clique. So what you can understand Gaussian elimination on a graph, eliminating nodes, is getting rid of nodes and putting cliques on them. OK, so I want to point out two great examples. If a node has degree 1, like a leaf of a tree, you eliminate it, you put a clique on its neighbor, but it's only got one neighbor. That's a self loop, and that disappears. So getting rid of nodes of degree 1 is essentially free. Nodes of degree 2 is essentially free as well. When I get rid of that node, I put a clique on its two neighbors. That's just an edge between them. And if you take a look at the time of algorithms in linear algebra for doing this, the time for an actual solve is the sum of the degrees that occur as you're doing your elimination Well, there's pre-processing, which is the sum of the degrees squared that you eliminate. So this is sort of why when you have trees, you can get a linear time algorithm, because you'll always eliminate a node of degree 1. So that is the graph theory of our classic Gaussian elimination. OK, so now you know that you can solve systems in trees quickly. And I told you I can approximate graphs by something like expanders. So it's not clear how that's going to help yet. So let me give you some trees that help. So let's go back to what Vaidya did. Well, he used maximum spanning trees. We're going to use the right thing for this problem. It turns out to be something called a low-stretch spanning tree. He can be excused for not knowing about it. It was invented by Loenkart, Peleg, and West in '91, so a year after his initial paper. But people didn't realize the relevance of it till Bowman and Hendrickson in '01 wrote this paper, where they said if you take a tree and you try to approximate a graph by it, the graph is less than or equal to the tree times, well, the stretch of the tree with respect to tree. Let me tell you what the stretch is. OK, the stretch of a tree with respect to g, we define this way. Let's say here I've got my spanning tree in black and a couple other edges in purple. For every single edge in the graph, there's a unique path in the tree between its endpoints. Take a look at how long that path is. In this case, it's length 6. That's what we call the stretch of this edge with respect to the tree. The stretch of a spanning tree is just the sum over all edges in the original graph of the length of their path in the tree. And this is the notion of this is sort of the measure or quality of approximation we use of a tree. Excuse me 1 second here. So Bowman and Hendrickson, as I say, pointed out the graph is less than or equal to the tree times the sum of the stretches.
So there's an edge in the graph which is not in the tree, and this has a huge weight.
There's a question about how to do this with weights.
Oh,
Sorry, I'm giving you the example with weights 1.
all right.
To do it right with weights, there's a weighted version of the formula. That is a good question. The short answer is you darn well better include that edge. If it has high weight. You'll see in a moment how to compensate for that, by the way. OK, so why don't I tell you what's known? Well, Loenkart, Peleg, and West showed that for every graph, there is a tree with stretch like m to the 1 plus little o of 1. So that's pretty good. It's near optimal. M log n would be optimal. And by the way, this was on a paper related to analysis of the K-server problem in competitive analysis, not something about graph theory at all. Sort of a miracle it got extracted from here. But this has been improved. A couple years ago with Elkin and Emek, we got it down to m log squared n, and in the next Fox, there's going to be a paper getting this down to m log n log log n. Probably you can get to m log n, but who knows? I don't see any good reason you shouldn't be able to. So this already gets you something pretty good in terms of solving linear equations. Because if you now plug in the preconditioned conjugate gradient, each of these linear equations in our approximation will solve in order n time. And then our multiplications, well, they're going to take order m time. And we're only going to do this, the square root of this stretch times. So that's going to be about m to the square root m times. And that gets us an improvement in solving linear equations. Let me show you a proof of this theorem of Bowman and Hendrickson. I'm going to do a very combinatorial proof. Their proof was playing with matrix norms, which is not as intuitive. So to prove it, you just need to know one inequality on graphs, and then we'll add it up together. If I just have an edge between two nodes, let's say I number them 1 and 8, and it's got weight 1. I compare that to a path with 7 edges between nodes 1 and 8. OK. The edge of weight 1, you can say, is less than or equal to 7 times the path of length 7. Generally speaking, an edge of weight 1 is less than or equal to k times the path of length k. And you can rethink of that as taking the path but blowing up the weight of every single edge by k, or 7 in this case. That is the one inequality we will leverage. Almost everyone learned this inequality in high school at one point. This is mathematically the same statement that if I take k unit resistors in serial, they have resistance k. Well, it is the same statement, though it might not be obvious yet. But once you put the right electrical interpretation, it is. And if you want to figure out how to generalize this stuff to weighted graphs, that's the same thing. And this is what people in the random walks literature talk about as Poincaré inequalities and exploit that way. So this is what we'll use. So what are we going to do? We're just going to take these inequalities and sum them up. So here's what happens. Again, when I
think in this
yes.
case, they still refer to it as Cauchy-Schwarz.
You can get it from Cauchy-Schwarz. It's not. It's a few lines from Cauchy-Schwarz, I think, unless you know a fancier derivation than I do. I need an induction around it, but we'll see. Maybe, yeah. Okay. I'll think about that. You'd be amazed at some of the complicated proofs of this statement. Anyway, so let's say I have a graph G and a spanning tree T, and let's compute some constant so that that constant times T is greater than or equal to G. Since it's a subgraph, it'll always be less than or equal to. So what we do is take an edge in G that's not in T, and I have this inequality. This edge, say I know it's less than or equal to 3 times the path of length 3 between its endpoints. That's my inequality. Keep the other vertices around. You just don't have edges on them, but keep the vertices. The way the proof goes is we sum up these inequalities. So I just take every single edge in the graph G. I get one inequality for each edge in the graph G. I have ignored the inequalities you get from the edges themselves that are also in the tree, because that's just a 1. You sum them all up. What do I get? In the end, when I sum up these inequalities, I get that my graph is less than or equal to some weighted graph with different times, or something like my spanning tree, but with different weights on all the edges. We just take the maximum of these. And certainly the stretch of the tree was an upper bound on the maximum of these. So that's what we will use. And that essentially is a proof that, if I take the sum of the stretches times the spanning tree, that's at least the graph. OK, well, fortunately for us, Vaidya's maximum spanning trees weren't nearly as good as low-stretch spanning trees. Why is that fortunate for us? When he did all this work and used maximum spanning trees, the actual algorithm he got wasn't any better than the conjugate gradient. So he needed to come up with another idea. His second idea was take a tree and add a couple of edges to it.
When you say maximum spanning tree, what are you maximizing?
That was, well, if it's unweighted, all spanning trees are the same. But yeah, he's more worried about weights, which you can sort of see is why some things go wrong. So we're going to use the same idea, but apply it to low-stretch trees. I've deleted the slides on exactly how, but I can explain them later if people want. But essentially what we do is we combine a low-stretch spanning tree with the sparsifiers I told you about before, with a linear number of edges, to get something we call an UltraSparse Afire. So this, I say, looks like a tree plus a couple edges. Here's one we did from this airfoil mesh. The way I think of it is it's n edges plus, well, OK, n over k is the parameter I'm going to control. There's some polylog term there. The constant sort of lowers every few weeks now, as people come up with better constructions of low-stretch spanning trees and sparsifiers and so on, so we don't know what it is yet. What you get when you do this is you get an approximation where the graph is less than or equal to k times the UltraSparse. So sort of you take a look that when you take, basically think of taking when you take a tree plus n over k edges, this term will probably become 1 in the end, or times log n. You get an approximation of order k. And that's what we actually use. And actually, all of this low-stretch spanning tree and sparsifiers for us really all goes into making these things we call UltraSparse. And if someone could give me a direct construction of these, I would be incredibly happy. There probably is one, but we don't know yet. So we're going through all this other machinery. We do all this in nearly linear time. Before I tell you about other fancy things in the talk, why don't I just tell you why this gives us an algorithm for solving linear equations. What happens is if I take a look at this graph, which looks like a tree plus a couple of edges, we make k big enough to swamp this out. So this is less than n. That means you have a bunch of degree 1 and 2 vertices. If I have a bunch of degree 1 and 2 vertices, I can eliminate them like I showed you earlier. And that only takes linear time. And when I'm done, I get a system of linear equations on fewer vertices. K is big enough to make this smaller than n. And then we use recursion to solve that system. So you actually approximate your larger system by a smaller system, and then you use recursion. And that's how we get nearly linear time algorithms. So here's roughly the statement. First, we just say, for any symmetric diagonally dominant matrix A and any B, you get a solution to the linear equations, nearly linear time, and I always put up for the numerical analyst, there are no other assumptions. We don't care if there's a differential equation underlying it, anything physical or not. Works on social network graphs or what have you. OK, I don't need to save time. So let me tell you now about how we construct sparsifiers. To tell you about how we construct sparsifiers, I have to tell you about graph partitioning and the measure I will use of it. And the measure that we use is the one called conductance. So how many of you are familiar with the conductance of a cut? Many, maybe half. OK. So this is, for me, one of the most fundamental notions to theoretical computer scientists. By the way, I actually go around and I give talks to numerical analysts, and I explain them why this is the same thing as the condition number, which is almost up to Cheever's inequality, which is, for them, the most fundamental thing. So if I have a set of vertices S, the conductance of the cut is, for me, the number of edges leaving the set divided by the sum of the degrees on the smaller side, or the number of edges touching the smaller side. I'll always consider the smaller side. Who cares about the bigger side? The smaller side is what's dominating. So I take the ratio of how many edges are leaving versus the sum of the degrees, or how many edges touch the smaller side. This is sort of a measure of how much of a cluster S is. If there are many more edges inside than leaving, then you say S looks more like a nice cluster somehow, because you want it to be more richly connected to itself than the outside world. We're also interested in measuring the conductance of a graph, which is the minimum of this quantity over all sets. So you often want to find the set of smallest conductance. Now, the reason that conductance is my favorite quantity in a graph is no matter what its value is, you can do something useful. Meaning, if the conductance is large, you have an expander. Or for our purposes, more importantly, we know that if the conductance of a graph is large, then we can do a random sampling procedure to sparsify it. Actually, our original proof of this was based on a variation of this argument of Ferretti and Komlosh for analyzing eigenvalues of random graphs, or random matrices, and sort of inspired by work of Akliopoulos McSherry. And the connection to go from conductance to these sorts of arguments, spectral arguments, you need to go through Cheever's inequality. But we know random sampling works. So very naive things work. Your graph is wonderful when it has high conductance. When it is low conductance, you're also in really good shape. It means you can remove not too many edges in the graph and partition it into two parts. Well, not if I say I don't have to worry about, remove a few edges that I don't have to worry about. Those sort of can go in my sparsifier. So fundamentally, the way we're going to sparsify is by decomposing a graph. We partition the vertex set, so we remove not too many edges, and each part has high conductance. And you can prove you can do that. There always exists a partition where, in this case, at least if that graph has a lot of edges. If it has few edges, we don't worry about it. It's already sparse. If it has a lot of edges, there's a decomposition where each cluster itself has high conductance and not too many edges cross the partitions. And if we have such a thing, then we can build sparsifiers. So actually, I'm going to tell you about graph partitioning just for the purpose of building sparsifiers. But what you would do then is you would do random sampling on these edges. And, well, these edges actually would treat recursively and build a sparsifier on those. So I'd sort of say, let's do random sampling on these. These ones you can recursively find sparsifiers on because there are fewer of them. And it doesn't run too many rounds. But the big problem is I have to do the graph partitioning. So now I'll tell you how. And that was a problem, because chopping up a graph like this is a little non-trivial. This is what led us to this local clustering problem, which I described again as, say, finding a vertex v. You start with a vertex v that's interesting in some large graph. You want to find a cluster near it. It might not actually include v when we do it, in time proportional to the cluster size, just by exploring from the vertex. So you look at its neighbors, some of its neighbors, some of their neighbors. We're going to worry about the conductance. We want the conductance to be small of the cluster. And the first question I'll ask you is how you should explore from a vertex. I think if I asked this question 15 years ago, people would have said, you do sort of breadth first search, or shortest paths. You look at the node, you look at its neighbors, you look at their neighbors, you look at their neighbors. We're now very aware that for most real-world graphs, once you do that, you'll have looked at every vertex in the graph. So that option is out. So you need a more intelligent way of looking at nodes that are near v you might do a little bit more work, but hopefully you don't load in the whole graph. So the way that Shang-Hua and I initially did this was by looking at nodes that were likely to occur in random walks starting at V. And we did an analysis of this actually using an analysis of mixing of random walks due to Lovász and Szymanowicz that appeared in a paper on volume computation. As I said, we wrote this algorithm we called Nibble that does this. I said, I won't tell you about our algorithm. I'll tell you about a better algorithm by Andersen, Chung, and Lang, which also uses the Lovász-Szymanowicz analysis, but theirs is based in PageRank, or something called the personal PageRank vector, which was mentioned in this initial paper of Brendan Page. Let me give you an idea of this algorithm. The idea, well, as I describe it, is vertices hold chips, or money, but chips is probably a better idea, which they're going to pass to their neighbors. For those who've seen chip firing games, this is natural. So vertices hold chips. They're going to pass them to their neighbors. But every time you pass some chips to your neighbors, you stick some in your pocket. It's capitalism. So you stick some in your pocket. You stick a p fraction in your pocket. Did I put that here? Yeah, so anytime you pass them to your neighbors, you stick a p fraction in your pocket. How do you decide how you do it? Well, you allocate of your chips. You save half for yourself in the pool that's not in your pocket, and you distribute the other half uniformly among your neighbors. But you only do this if you have enough chips to make it worthwhile. There's some parameter epsilon governing that. You only do this if you have more than epsilon times your degree number of chips. OK, so this is sort of an example. This thing has 0.14 chips, this node. It's going to stick 1/5 in its pocket, 0.028. And then send, of the remainder, it keeps half for itself and distributes the other half equally among its neighbors. These two parameters, p and epsilon, control fundamental things. The smaller epsilon is, the more nodes that you'll actually examine in this process. That's because we say you only send chips to your neighbors if you have more than epsilon times the degree. So as you decrease epsilon, you're more likely to send chips to your neighbors. Otherwise, you just stop. The smaller p is the lower of the conductance of the cut you're looking for. That's a less obvious connection. So the suggestion of this paper essentially is you explore a graph by starting with all of your chips on one vertex, and you run this process. What I love about this process is it doesn't require any assumptions of synchrony or anything. You can make the vertices do this operation they call a firing or push operation at any time you want, as long as they're above threshold, unlike the operation Shang-Hua and I did. So this means you can optimize for cache performance and do all other sorts of fun things. So let me give you an example for those who haven't seen this. Here's my graph. Well, here's part of my graph. I have one node we're going to start at. It's got all the chips. I know this part of the graph. Here's some sort of boundary edge, and who the heck knows what's out here, but let's assume this is the rest of the people in the United States over here. Now, if you think about what you'd like to do, before you start talking to the rest of the people in the United States, you'd like to make sure that you've explored this portion of the graph. And that's what'll happen. So if we take a look at this node starts out, as I say, it's going to keep 1/5 for itself, move the rest to its neighbors. And OK, so it's got 0.2. They've each got 0.1. So now we can actually pick any node to do this with, as long as it's above threshold. My threshold is 1/50th times the degree. So I could do any of these nodes, but I may as well do the middle node again. Actually, I could do all the operations on the middle node at once, but it gets low enough. Let's say we pick this node. This is the amount it has in its pool is above threshold, so it'll move some into its pocket, some to its neighbors, and some back to here. That's a little bit annoying. You're doing some extra work because you're going back to that node again. But we're doing some computation to try to save exploration. Keeps going. We could do that node up top. Eventually, you might do the node in the middle again. Well, you sort of have to eventually, because until it's below threshold, you'll want to do this operation.
What decides which node you have to, or does it
Actually, it doesn't matter. All you need is that any node, when it is above threshold, says, I'm going to do this operation eventually. But you don't need any real guarantee. You don't need to synchronize it. You don't need any global control. As long as you do this, you're guaranteed not to explore too far or go too far afield. The annoying thing is you do keep coming back to some nodes many times. And one of the big problems in the area is how to stop that, because it's frustrating. OK, so here I took us to step 15. As of step 15, you'll notice almost any node that has done this firing operation has put something in its pocket. And every single node has, except for this node here and this node up here. An interesting question to ask yourself is, can this node do this firing operation? Well, the threshold, it has to have at least degree times epsilon, which would be degree times 1 over 50, which it doesn't. Its degree is 3. So that one isn't going to be able to fire. But this one could still fire. This one can't fire. Oh yeah, that one can just barely fire. OK. I think. Anyway, so if I take this through all the way to step 24, where you ended up with, so you wind up having explored only these 9 nodes. It took you 24 steps, which might be a little bit annoying. But at least you didn't go into the rest of the graph. You never actually fired this one and never touched this node. And that means the process actually stayed local. If you decided that you had to explore further, what do? You lower epsilon. And this is how you wind up exploring in a graph, according to this idea. Now, how do we wind up partitioning? Well, OK, if you just did this, there's a very natural idea of partitioning. Take all the nodes that fired. But that turns out to be a little too crude, though it's good here. Because here you just cut right there. Generally, what you do at this point is you order the nodes by how many chips they stuck in their pocket. So this node had the most in its pocket, and you can see the numbers going around. And then you look for a cut in this prefix of this order. So you take, let's say first, what if I take the node that has the most? That's not a very good cut. Take the top 3. Well, you take the top 2, the top 3, the top 4, and so on. None of them are very good cuts until a little further on. Once I take the top 8, this isn't such a bad cut. I wind up cutting this edge, and that edge. Sometimes the outputs are going to look like that. In this case, I, of course, rigged the example. So the best cut is this one. And this is the cut of lowest conductance you get. But you do it by taking the vertices in this order and take a prefix. So that's how it works. They prove some theorems for it. I'll give you a rough idea. There are many parameters in these theorems. So one of them is this. Like, if there is a set of conductance less than 1 over log to the 4th n, if you started a random vertex of that set, then you probably output a set C with conductance that's small, 1 over log n, let's say. The nice thing is the set C mostly lives in S, and you do it in time proportional to the volume of that set, times log to the 4th n. The high powers of logs are a little annoying. I don't know if they're an artifact of the analysis or necessary yet. The one thing I can say for their algorithm is you can guarantee that the number of nodes it looks at is at most 4 times the number of nodes it's going to output. So even though it's doing a heck of a lot more work here with this log to the 4th, it doesn't actually examine too many nodes, which is probably the dominant cost to just pulling things into memory. We use this for some sort of approximate cut algorithm. So you sort of just do this, and you do it again, and you do it again, and you do it again. You keep removing chunks until you can't do it anymore. And you remove things. And what you get is basically the algorithm approximate cut, if it outputs a cut, you have a guarantee on the conductance of the cut it outputs. It's the most phi. And we also know that if the cut is highly unbalanced, if we output a small set, then we know that the complement is contained in a graph of large conductance. A little bit worse. You get like phi squared. For comparison, if we took the optimal cut, if you took the sparsest cut, and you knew it was small, then you can prove that the complement is an expander, or has high conductance. Here we can't do that. But here we can prove at least the complement is contained in a graph, which is an expander, which is about as good as we can hope for right now. OK, so that's enough about graph partitioning. I don't have that much time left, so why don't I just give you some highlights of other things that have been done in this area. So first, as I said, I mentioned interior point methods earlier. If you look at solving a family of linear programs, like maximum flow, multi-commodity flow, what have you, with interior point algorithms, when you do it, you keep solving the linear systems you get are always very special. So if you're solving maximum flow, you always get diagonally dominant linear systems. Same thing with min-cost flow. So Sam Daitch, who's a graduate student working with me and I, took a look at interior point methods and said, what happens if we solve these systems approximately? Took a little bit of retooling of the interior point algorithms, but with a little work, you see that you get they work with only approximate linear solvers, and you get fast algorithms for things this way. So like for max flow and min cost flow, we get order m to the 3/2. Well, there's some log terms. So asymptotically, that's almost as good as the best max flow algorithm of Goldberg and Rao, and it beat the previous best min cost flow algorithm. We looked at generalized flow. This is a flow problem where the amount that flows into an edge is different than the amount that flows out. You've got some gain or loss factor. And then it turned out the linear systems were all these things called M matrices, which have been studied for about 50 years in numerical analysis. And they come up in economics and a bunch of other cases. And we figured out, or Sam mostly figured out, how we solve those. And that gets us fast algorithms for generalized flow. And my hope is that people will extend this chart. I think that for a lot of algorithms that people do solve, or a lot of problems people solve by using linear programming, if you study the linear equations you can get faster algorithms for them and thereby throw it into an interior point method and thereby get faster algorithms for the original problem. My next hope is that someone will do this for multi-commodity flow, which would be very interesting. The other fancy things have been used. So first, Gremban and Miller, and then a paper of Maggs, Miller, and many other authors, and a couple others, looked at actually adding vertices to your graph and approximating it. So for example, they'd take an initial graph and then build a tree on top of it. And there's a notion that you get for this of approximation with a graph with more vertices that makes sense, and you sometimes get faster algorithms. There are two ways to say what you get. One of them is to get the right quadratic form just on the original set of vertices. You either choose always the minimum value for the other vertices, whatever minimizes the quadratic form. Formally, you can say it's what you get by doing Cholesky factorization and eliminating those nodes. That induces a graph on the rest. And then you can measure quadratic forms. But when you do that, your system with these more vertices might be much simpler. Like they looked at using trees. And they were inspired by work of Harold Rack to do that, and first used the Rack trees in one of those papers. They also, Miller and Koutis, looked at a case where they used fewer vertices. They sort of cluster vertices together. And this got them a linear, and with some work, then they get a linear time algorithm for solving Laplacians in planar systems. So that gets rid of all the nasty log factors that we had. It's a nice result. Shklarski and Toledo looked at splitting vertices. They actually talked about taking a vertex and splitting it, and then its edges get shared among the copies. And they looked at they introduced this to try to solve linear equations that occur when you're doing structural dynamics, at least for two-dimensional truss structures. And Sam Daitch and I finally did the analysis that using this and then preconditioners, like I showed you before, we can speed up solving truss structures or doing linear equation, at least two-dimensional truss structures. We get to like end of the 5/4. Three-dimensional truss structures, there's some combinatorics we don't yet know how to handle. The algebra, I think we can do. OK, so why don't I just give you a bunch of questions that arise from this work, a lot of things that need to be done. First is, what else can we do with local algorithms? Or what else do we want to do with local algorithms? Like, everyone's got massive graphs. I'm sure many people have nodes of interest. For me, the first thing I ask is, can you find a cluster around that node? Reed Andersen, you should look at his homepage, has done some good work on finding communities and other things. But there must be a bunch of other problems you might want to solve this way. I don't even know what they are. Probably people at Microsoft have a better idea than I do. But I think it's a very good paradigm for designing algorithms. It makes sense, and there's some interesting tools for it. The next thing I want to do is some fast and practical sparsification. As I said, I've had a team of students come up, try to implement all sorts of different heuristics for doing graph sparsification. The best of them is now here at Microsoft as a software developer. I'm really still trying to drag him to graduate school because he's a brilliant algorithms engineer, I think. But he came up with a lot of heuristics, and I say usually for any graph one of them works, but we don't know how to pick it in advance, so it doesn't help us yet. Faster low-stretch spanning trees. The constructions of these things right now are actually like n log squared n or n log cubed n, and it turns out that's a bottleneck for us, at least if we want to solve linear systems under about 1 million, 2 million vertices. That's a bottleneck if we try to do this stuff. So we use other heuristics right now. I say direct constructions of UltraSparse Afires. If we could get that, that would be really handy. I could drop these previous two things. And when people want, I can tell them how we build them, but it's a bit hairy. It turns out, actually, for a lot of our applications, we don't necessarily, well, unless we get to linear systems on about 10 million vertices, it's not a win, and we can substitute with something simpler. Above about 10 million vertices, we really need these UltraSparse Afires, and we just don't have a quick algorithm for them. So say, what other types of linear equations can we solve using these ideas? There's a lot of them. I'm sure people get different types of linear equations in different areas. I will say the one thing we need is we got to have some combinatorics. It has to come from a well-structured problem, meaning you have to give me a good reason that the system is not singular or degenerate. Like with linear equations and Laplacians, if the graph is connected, we know what the null space is. Or you need to combinatorially understand the null space. With stiffness matrices and truss structures, we know what they are. With interior point methods, there are combinatorial reasons why these things are not degenerate. If you can't tell me why your system shouldn't be degenerate, then I can't help you solve it. But if you can give me some combinatorial reason that it's not, then that's something we can work with to try to solve it. And finally, the last question, well, this is less on this talk as some of my others, is what can we do towards making all this linear equation machinery practical? We've done a decent amount of implementation work. We beat a heck of a lot of our competitors, all the ones we've been able to compile. But still, there's a lot. There's some we can't compile that we know beat us, but stuff built by folks at the national labs that run on their machines. But there's a lot to do here. And I think it's actually an interesting problem. Especially the sort of linear equations that might come up if you're taking a look at trying to analyze social networks. And I guess I briefly mentioned one application we can do for you is, by solving a couple of linear equations, we can compute the effective resistance of every single edge in a graph. Or actually, for every pair, we'll get you a data structure that you can use to query the effective resistance between any pair of nodes. Which seems like a useful thing, because it's a very handy measure of how connected two nodes are. To do that, we only need to solve a couple of linear equations. So if people want to do that, we're happy to gear up and do it for them, or at least take a look at the types of graphs they have and see if we can give an advantage on it. And I think I'll stop there and take any questions. Yeah.
Do you have any nice lower bounds on the stretch?
Yeah, you can't. Oh, I should tell you. Actually, you can't do better than n log n. An expander is a lower bound on that. So if you have an expander and you try to get a tree, you're going to have at least total stretch n log n. And even a nice example, and that every edge will get roughly n log n. There are also examples where some edges have to have high stretch. For example, if you take a cycle, try to get a tree, you're going to have, the edge you drop out is going to have stretch n.
Let me give you a specific example I have in mind.
Okay.
Suppose you took a binary tree, irregular tree up
sure.
some distance, and then cross it with a cycle.
Take the product with a cycle.
Or an interval, long interval.
Interesting question. I'm not sure, but we can check. That can't be hard. When I say that can't be hard, there's also a lower bound for the grid of n log n by Gary Miller and I forget who now, I'm embarrassed to say. So it might be you can't do better than n log n, because grid is just a path cross a path. If you give me a tree cross a path, I don't know we're going to do any better. But there's a small chance you can do better.
But are there any graphs where you think or expect that the lower bound will be bigger than that?
No, I actually think n log n is a lower bound, and I have good reasons to. It's a lower bound and an upper bound. Right, it's an upper bound. Yes, I have good reasons to think we can get there, but I can't prove them yet.
Does it follow from the symmetric embedding that the upper bound is n log n for any graph?
No, I don't. We don't know. The best we know is this n log n log n. We don't know for every graph there exists a tree of n log n. The best we have is this result of, is it Abraham, Bartal, and Nyman right now? Yeah.
What if you just ask for tightness of the distribution of the stretches, not just the maximum?
It doesn't help you. So just by taking linearity of expectation, if the distribution of the stretches comes out right, then there's one that's expected to come out right. Or, so if you want every stretch to be expected log n.
No,
okay, I'm sorry.
Just the distribution. So you look at a pair of neighbors in the original graph.
Yes. Oh, you're looking at the distribution. Okay, so if you take a look at a pair of neighbors.
Right.
Typical pair of neighbors.
Oh, if you want a typical. Oh, I understand what you're asking.
I don't know if that's useful for you or not, but it's relevant.
For a typical pair of neighbors, you can make the stretch smaller. So if you take a look at the analysis of the construction that we did and then that Bartal et al. Improved For almost all neighbors, the stretch between them winds up being lower. It's just that there could be a couple exceptional ones that are big. I can explain later how the construction goes, but it would be fairly clear.
If you have lower bounds.
Oh, lower bounds on that.
In some special cases like I mentioned.
Ooh. No, but we could think about them. I mean, yeah, that. Sit down, give me some examples. We can probably. I mean, some of the lower bounds are tricky to make. The lower bound for the grid was non-trivial, but we could probably exploit it. Yes.
So this may be a basic question, but
Sure.
since you gave this definition of approximation, that kind of implies that you're giving a definition of distance.
Yes.
And
Okay.
So I wondered if that definition that you gave of distance is like really standard, it's the definition, or and how.
That's okay. So that is a good question. Okay, so let me remember here the right answer to this. So if you take the log of the condition number, that's a reasonable notion of distance. I mean, the condition number itself isn't, because it's always bigger than 1. But the log of the condition number is always at least 0. It obeys the triangle inequality. And I once proposed this as a definition of distance. And my former graduate student, John Kellner, explained to me why this is the wrong notion of distance. And if you ask me later, I can call him up and find out why. I vaguely remember that if you look locally around a matrix, there is an exact right notion of distance, or something that locally looks sort of Euclidean. And this was not it. So I forget why, though. But there is a right notion. This is let's say this is a reasonable notion of distance. I don't remember why it's the wrong notion, but there is something you can express that at least locally on matrices is supposed to be the right distance, at least on positive semi-definite matrices. Someone else may be able to tell me the right notion of notion on positive semi-definite matrices, but there is.
Wouldn't you?
Yeah.
I mean, if you do a breadth first search of the graph, then wouldn't you be getting the lower bound? Given
Oh, you mean for the
lower
like?
bound for the
Oh, no, there are things that are much better than breadth first search for constructing like these low stretch spanning trees. So the breadth first search trees don't help us much. I mean, actually, the best way that I compute them empirically is finding separators in the graph, decomposing the graph into 2 parts, recursively finding a tree on each, and then I can use dynamic programming to choose the best edge to add between the 2 of them. Empirically, that works, but experimentally, you can't prove much about it, and I know a lot of people have tried. And then you have to resort to using graph partitioning code that slows it down a little. But yeah, breadth first search trees, there are some graphs in which they're good. But, well, the problem is there are too many of them. You can make them that look like, on the grid, it could, if you're unfortunate, look something like this, which has very high stretch. That has very high stretch, whereas the right thing on a grid sort of looks like this tree with H's in it. And it goes in a sort of fractal way like that. And we don't know anything better.
But if you use breadth first search, starting from each node, then eventually you will come to this H tree.
Well, it's not clear to me, but maybe if you hook them up the right way, but you have to be a little careful how you hook them. I mean, I will tell you the original algorithm of the Lone Carp-Pelican West did work by growing breadth first search trees out to a small radius and then eventually condensing those down together and then hooking them up, then sort of recursively repeating this process. It was a bottom-up process, doing local clustering and then grabbing things and clustering them again. And you could see how that would get you something like that. But they had to be careful to restrict the growth to not go too far in any one breadth first search tree. And then there were problems with these things overlapping and biting off different chunks of the graph. But that is sort of how the first algorithm went. The algorithms that seem to work best use a top-down approach, at least so far. They sort of do some sort of graph partitioning and then do something in each part and then add edges to hook them up. But we can't do it partitioning the graph into 2. We have a somewhat fancier partition of a graph that we start with.
Is LA Pac on the ones that you compile?
I'm sorry, say that again?
Is LA Pac on the ones that you
Oh, no, LAPAC we use. No, the fancier things that I can't compile, or, well, in theory, by the time I get back, one of my graduate students will have this compiled, but the algebraic multigrid codes, we've had trouble getting to work. There are a number of them, but all the packages seem to require something that you either have to twist our sysadmin's arms to install, or then they conflict with each other. So, but no, LAPAC we've got working nicely, thankfully. But yeah, no, LAPAC doesn't go that far. Yeah, so there's this other approach called algebraic multigrid, which is this approach towards preconditioning and doing a multi-level thing. It looks a lot like ours, and it works very well for things that come from partial differential equations. And it seems to work not as well for things that come from stuff like social network graphs, as far as I can tell. At least I can think of no reason that it should. And people tell me they have trouble with it in various cases. So one of my students spent last summer at Argonne National Labs trying to fix things up. But as I said, we can't run all of the code that he used there on our machines yet. So we don't know the full deal yet.